Assalamu alaikum, dear student. My name is Dr. Muhammad Adnan Asghar, and today the topic of our discussion is characterization of pharmaceutical materials by using thermal analysis under the subject of thermal analysis. So far, we have discussed some of the important applications of uh, different compounds, and we also sought out and explored some of the important applications by using different thermal techniques. While in the case of pharmaceutical materials, so far we have discussed about the conventional diffraction scanning calorimetry along with the modulated diffraction scanning calorimetry, and in last lecture we have discussed some of the advantages of modulated diffraction scanning calorimetry over the conventional or traditional diffraction scanning calorimetry. In this lecture, we will discuss some of the pharmaceutical applications by using the thermal analysis. Because all transitions in materials involve the flow of heat. If we talk about transitions in materials, these transitions are of many types. For example, the transition may be from solid to liquid. For example, solid is a phase, and the shifting of a solid phase into the liquid phase is actually the transition of that solid phase into liquid phase. And sometimes the liquid phase into a gaseous phase or its vapor phase. So sometimes liquid solid directly change into its vapor phase without passing through its middle stage, which is the liquid one. So these are the different type of transitions. Somehow the most important one is actually the solid to solid transition. How we can say this is a transition, solid to solid phase transition? It is actually happens when one of the solid possesses two different forms at two different temperatures. For example, in last lectures we have studied about the phase transition materials. In phase transition materials, we can see that if one compound have phase transition property, for example, at about 250 Kelvin, then we can say that this particular compound have different structures below and above 250 Kelvin. So, how we can measure all these kind of transitions? We know that all kind of transitions are in materials are actually the flow of heat that is into the sample during the endothermic events and from the sample for exothermic events. Diffraction scanning calorimetry is the universal detector for measuring a wide variety of transitions in pharmaceutical materials. This lecture would actually focus on some of the most common measurements, and will definitely will describe the superior performances of T0 diffraction scanning calorimetry and modulated diffraction calorimetry, and we have already discussed some of the important aspects of T0 diffraction scanning calorimetry and modulated diffraction calorimetric technologies. These applications actually include the measurements of Amorphous structures. Amorphous structures includes actually the glass transitions. We know that glass is a amorphous compound which possess the amorphous structure and it is not regular fashion. The detection of amorphous material in semi-crystalline compounds. The second one is the crystallinity. Uh, this would help us to measure the melting and crystallization, moreover purity and polymorphs. We have already discussed some of the important aspects of crystallinity in our previous lectures, where we studied that we can find the melting point of any particular compound by using TGA, thermogravimetric analysis, along with the DTA, diffraction thermal analysis. These two techniques are actually used together to find the exact melting point of any particular crystalline material or amorphous compound. And moreover, it would also help us to find out the crystallization temperature of many inorganic compounds. The purity, of course, is an important thing. It would also help us to find out the impurity of the sample, and the polymorphs, the different forms of the crystal, can also be detected by using different thermal techniques with coupled some of the renowned other techniques including uh, dielectric measurements. The third one is the drug interactions. We can also find out the drug interactions by the help of thermal analysis, and we will discuss in detail in our next lectures. The protein denaturation along with freeze drying and many miscellaneous or complementary type thermal analysis techniques. So first of all is the amorphous structures. The physical properties of amorphous structures are quite different from crystalline structures. Major differences include dissolution rate, faster bioavailability, storage stability, and hygroscopicity. The tendency to absorb moisture or other solvents. Hygroscopic property is actually the ability to absorb moisture contents or some solvents from the atmosphere. It is therefore important to know if a drug or drug delivery system has an amorphous component. The most common diffraction scanning calorimetry measurements of amorphous structure is the measurement of the glass transition. It is important to know both the size of the transition in heat flow or heat capacity. It is imperative to understand both the size of the transition in heat flow or heat capacity units and temperature at which it occurs. The temperature may be called as Curie temperature, sometime Tc and represented with Tc and sometime by Tg. The size of transition provides quantitative information about the amount of amorphous structure in the sample. The temperature identifies the point where there is a dramatic change in physical properties. Below the glass transition temperature, there is limited molecular mobility, while above there is high mobility that results in much lower viscosity and potentially much greater chemical interaction between components. Because of this, there is general desire to store sample at least 40 degrees Celsius below their glass transition temperature. It is actually a kind of temperature, the glass temperature, which is denoted with Tg. It is a kind of temperature at which amorphous compound actually shifts one of its phase to another one, which is quite different from the glass amorphous glass compound. So if we talk about the Tg, which is actually the glass transition temperature of a particular amorphous compound, it actually the below the Tg is would be represented with the low temperature phase of that amorphous compound, while in the case of above the Tg, which is the glass temperature, the above phase would also be known as high temperature phase, HTP. So that actually this glass transition temperature or this glass transition uh, would triggered with the help of different types of stimulus. These stimulus may also be known in the form of mechanisms. So there are some mechanisms behind this glass transitions. The mechanisms may be of order disordered in nature. The maybe it's maybe of displacive type of glass transitions, and sometime proton dynamic motion that would occur in that particular compounds. More importantly, the more importantly the actually the order disorder phase transition or glass transitions are uh, quite renowned, because the below phase transition point or below glass transition Tg point, the molecular motion of that particular compound would freeze, and the motion of atoms in compound may have restricted displacement in a small range of area, while increasing the temperature above the glass transition would facilitate more rotational motions or vibrational motions of the molecules, which is actually the sometime disordered state of the molecule. So the actually this may be the possibly mechanism of these type of compounds. Below the glass transition temperature, there is limited molecular mobility, while above there is high mobility that would result in much lower viscosity and potentially much greater chemical interaction between components. So this is the reason to store these type of materials uh, at least 40 degrees Celsius below their glass transition temperature. Since amorphous materials are often hygroscopic in nature, and because small amounts of moisture or solvent act to plasticize the sample. It is important to measure the actual TG, which is the glass transition of drug formulations, as well as to control their volatile content. In this figure 3 shows the glass transitions of an amorphous sucrose sample that was exposed to lab air for about 30 minutes. This sucrose is actually exposed to atmospheric lab atmospheric temperature pressure for about 30 minutes. The first heat flows shows that the midpoint of the glass transition centered near 28.7 degree Celsius, while the second heat to 100 degrees Celsius shows that it has increased by nearly 40 degrees Celsius to 11.8 degrees Celsius. Even this sample still has several percent moisture, since the glass transition of completely dry sucrose is nearly 70 degree. While in figure 4 is an modulated diffraction scanning calorimetry experiment that actually shows how the size of glass transition increases with increasing amount of amorphous structure. The sample of polyethylene terephthalate, which is also denoted PET, was first quenched, cooled to produce a 100% amorphous structure, then cooled at slower and slower rates to produce increasing amounts of crystalline structure. Even with a cooling rate of about zero point 0.2 degrees Celsius from above the melting temperature, the material retains a large amorphous component. To quantify the percentage of amorphous phase, the size of the glass transition may be divided by the size of the glass transition for 100% amorphous sample. Although uh, this is a good approximation of amorphous content of the sample, the actual content is probably slightly higher. We can even use a formula of percentage amorphous phase, which would be equal to 0.14 over 0.35 into 100, and which would be equal to 40% of that particular amorphous phase. Amorphous material that is sometimes trapped within crystalline lattices, often called the rigid amorphous phases. It actually does not contribute to the step change in heat capacity at the glass transition, and it is therefore unable to detect. One of the most difficult measurement for diffraction scanning calorimetry is actually the detection of small amounts which we can say the less than 5% of amorphous material in the highly crystalline samples. This is one of the most difficult measurements that diffraction scanning calorimetry can perform. The transition is small and in often hidden by small variations. The small variations may be non-linear in diffraction scanning calorimetry baselines. Uh, for example, this figure 5 shows the results of actually the outstanding baseline which is obtained with T0 diffraction scanning calorimetry on a sample of crystalline sucrose that has less that has less than 1% amorphous phases. So this is the actually the T0 diffraction scanning calorimeters have some of the advantages. For example, it is actually uh, figure shows that duplicate how duplicate runs on a very small sample. This very small sample means we can even take 180 micrograms of the sample of freeze dried amorphous sucrose. The value of the second heat is to not only check the reproducibility but also to verify that sample is dry. A wet sample, even with a few percent moisture, would have a lower glass transition temperature the first time that is heated in a crimped pan. These runs are essentially calibration runs for determining the weight of the amorphous material in another sample based on the size of glass transition. The first experiment was actually on a relatively large sample of sucrose. The large sample of sucrose means 15 milligram that was thought to be 100% crystalline. Large sample was used to increase the sensitivity of the measurement in detecting small amounts of amorphous contents. At the expected glass transition temperature, a very small amounts of amorphous contents. As expected glass transition temperature, a very small step change of 8 microgram is detected. Comparing this change with that of 100% amorphous sample, which actually permits the calculation of the amount of the amorphous structure in the crystalline sample. In order to verify that there are small amounts of amorphous material in the crystalline sample, the technique of standard addition was applied, uh, where a known quantity of amorphous material may be added to a known quantity of the crystalline sample. For many samples, it is often difficult to detect the glass transition by diffraction scanning calorimetry even when the sample has a higher amorphous content. This is due to the interference from other transitions that occur over same temperature range. Because this is actually an modulated diffraction scanning calorimetry experiment, the transitions are separated into the reversing and non-reversing signals and can more easily interpret it. So this is all about this lecture, and we will discuss some of the important aspects of pharmaceutical measurements by using thermal analysis in the next lecture. Thank you very much.